Good afternoon, class. We are looking at statistics, module 5, covering chapters 10, 11, and 12. Here's chapter 10, correlation and regression. Could somebody read this question, please?
Given the sample data, find the value of the linear correlation coefficient R. B, test the claim that there is a linear correlation between the two variables x and y. Use both A method 1 and B method 2, with alpha being 0.05. Find the regression equation is C. D, find the best predicted value of y when x is equal to 2.
Perfect. So let's see what we need to do first by looking at a couple of things here. What is a scatter plot and what is the strength of a linear correlation R? A scatter plot is a graph of the ordered pairs x, comma, y. X, the independent variable, and y, the dependent variable, the same variables that you're familiar with from algebra. So you plot the pairs and you try to make up a line going through them. In this case, as you can see, it has a positive correlation simply because the slope is positive for this line. Distinct straight line or linear pattern. We say that there is a positive linear correlation between x and y, since as the x value increase, the y corresponding value also increase. If there is a strong positive linear relationship between the variables, the value of r will be close to +1, normally 0.7 or larger. In other words, as you can see in this case, x increases, so does y. In this case, we have a distinct straight line or a linear pattern. However, the slope is negative, as you can see. We say that there is a negative linear correlation between x and y, since as the x value increase, the corresponding y value decrease. If there is a strong negative linear relationship between the variables, the value of r will be close to -1, like -0.7 or smaller. There is no pattern here. And again, let me just write this one for this case. As you can see, when x gets larger, clearly y gets smaller, and that gives rise to the negative slope, and therefore negative correlation. If there is no distinct pattern, as we can see it here, which suggests that there is no correlation between x and y. So normally in this vicinity, when we calculate the linear correlation R, over here, no linear correlation. This is a positive strong one, 0.7 or larger, from -0.7 to -1, strong negative correlation. However, correlation doesn't imply causality, doesn't mean that it caused it. So things may be correlated, but one may not cause the other. So going back to the question, first and foremost, I want you to know most questions like this are not done by hand. The only reason I have picked this question, we don't have many data, so I want to show you how it's done by hand, but you don't have to worry about this being done by hand. R has a very complicated formula, n summation of xy minus summation of x times summation of y, square root of n summation of x squared minus summation of x quantity squared times n summation of y squared minus summation of y quantity squared, the whole thing under the radical. And so if we want to follow this formula, let's see what we need to find. First, let me write x and y again. Column-wise, it makes it easier. So when I look at this formula, I need to multiply x times y. So 1 times 2 goes here, 2, 1 times 8 goes here, 8, 3 times 6 goes here, 18, 5 times 4 goes here, number 20. Then summation of x and summation of y simply means add this up. So that is not a big deal. Add this column, write it here, add this column, write it here. Summation of x squared. Well, here's x. Let's square it and put it here. When I square 1 and 1, both of them are 1. 3 gives you 9, 5 gives you 25. So this is the next column. Again, I'm explaining with details how we arrive at it. Y squared. The reason I'm looking at that because I need the summation of y squared. So let's do that. That means this column squared, 2 squared becomes 4, 8 becomes 64, 6 becomes 36, 4 becomes 16. And now we need sum of each column. So add these numbers, put them here. That would be summation of x. Add them up. Summation of y. So this summation of x, summation of y. This one, summation of x times y, which is this one. This one is summation of x squared. This one is summation of y squared. So let's add them all up. Again, showing you all the steps. Now, the next one is to use this formula and plug in. N, we have 1, 2, 3, 4 pieces of data, 4 pairs. So N is 4 times, plug in, see what you get. Summation of x, y is 48, minus summation of x times summation of y minus 10 times 20, over the square root. N again is 4, summation of x squared is 36, minus summation of x, which is 10 quantity squared. We want to distinguish between summation of x and then square it versus summation of x squared. The next one is the same thing, but involves y. N is still 4. Summation of y squared is 120 minus summation of y, which is 20 quantity squared. And when you put it to a calculator, the top is minus 88, the bottom is square root of 44 times 80, and it becomes negative 0.135. Normally we use more decimals, but just in case. So this is done by hand, and we have only 4 pieces of data, so it's manageable. We never do this by hand. So what do? So you enter the data into L1 and L2, and I'm reminding you how to do that. And then we run linear regression t-test, and we enter L1 and L2. The x's enter L1, the y values enter L2. Okay, 1135, 2864, and we run the linear regression t-test. It gives us a lot of information. For now, I'm just interested in this. There are other informations, we'll see that in the next page, but for now, the only thing I want to show you is that this R that we calculated here, of course, with a lot more decimals. All you have to do, L1, L2, run this by putting it. It gives you L1 and L2 unless you want to change it. And rho is not equal. Then calculate gives you all the information you need. And this is another calculator online. Some of you are familiar with that. So let's run the test of hypothesis. And again, I'm going to show you that test of hypothesis has 4 steps: null and alternative hypothesis, test statistic, then critical value, which results in rejection region and non-rejection region, and we make a decision. Again, I want to show you how it's done using previous chapters. So the very first step, we write H0, rho is equal to 0. H1 rho is not equal to 0, which makes a two-tailed test, and that is the claim. This means if we reject H0, we go with H1, and that represents that there is a correlation. If we reject H0, there's a correlation. And I'm reminding you from the previous page, we have n equals 4, and we calculated R to be negative 0.135. There are two methods. For test statistic, we can use this formula, and on purpose, I'm showing you this formula also. These two are identical, and I hope you recognize that this is algebra. By the way, mu sub R is the same as rho, by the way, and comes from H0, and it's always 0 for us. So this is always 0. So we plug in. We have the value of R. We plug it in. We have the value of n. We plug it in, and we let the calculator do the math. So negative 0.135, the square root of 1 minus negative 0.135 squared over 4 minus 2. And we end up with negative 0.1927. For the second method, we just use the value of R as test statistic. Then the distribution, with the method 1, we use the t-test. Alpha is 0.05. Degrees of freedom for correlation is n minus 2. So 4 minus 2 is 2. And if you look up the table or use technology, t ends up being plus minus 4.303. The second method uses the critical value from Pearson correlation coefficient table. We also have that table in our last module of Canvas. N is 4, alpha is 0.05. In both cases, I will show you on the next page how to get that. So the critical value from this table is plus minus 0.950. If we were to do the drawing, and we must in order to make a decision, here's your t-test, here's your critical values, minus 4.303, positive 4.303, and here's your test statistic. Where does it end? Way into the non-rejection region, the first format. The second format uses a different methodology, a different table, again, Pearson correlation coefficient. You draw simply a line, just a number line. On this number line, you put the two critical values, negative 0.950, positive 0.950. It's a two-tailed test. The two tails are the rejection regions. And the number that you have here, R, is negative 0.135. It's somewhere here. It's between the two values. It's way into the non-rejection region. So how do we make a decision? Do not reject H0. So if you're not rejecting H0, what are you rejecting? You're rejecting H1. So the claim becomes false. And therefore, there is no linear correlation between the two variables. And I want to emphasize this. When we run the test for the correlation, whenever we reject H0, there's a correlation. Otherwise, there is no correlation. What I want to show you the critical values and how we got that from the two tables, reminding you about the t-test and showing you this table. This is a portion of the t-table, everybody. T-test, alpha is 0.05, degrees of freedom n minus 2 equals 2. Let's find those numbers. On the left column, we find the degrees of freedom. Up here, area in two tails, because correlation is always a two-tailed test. You put them together, the answer is 4.303. And because you know it's a two-tailed test, t is plus minus 4.303. If you want to go with the second method, you have to use Pearson correlation coefficient R. And again, the information from the previous page, n is 4, alpha is 0.05. Put them together. What do you find? 0.950. You know it's a two-tailed test. Therefore, the critical value based on Pearson correlation coefficient is plus minus 0.950. I just wanted to show you how I got those numbers, those critical values from the tables, the two tables. Let's continue. We want to find the regression equation. Again, all of this is done by technology, but I want to show you how it's done by hand. When we say regression equation, we are going to the basic algebra of y equals mx plus b in short, and m is the slope, as you recall. So some calculators, they use y hat is b sub 0 plus b1 x, and this is the slope. Some use y hat equals a plus bx, in which case b is the slope, remember that. And so it tells you how to calculate the b1, the slope here, and then the y-intercept. So since we have done all of these calculations, and again, I picked it up from the previous page, n is 4, r is negative 0.135, and we have all those summations, we can use this formula. N is 4 times summation of x, y, which is 48, minus summation of x times summation of y, 10 times 20. Again, I'm using this formula. N again is 4, summation of x squared is 36, minus summation of x, which is 10 quantity squared. And when you do the math, you end up with negative 0.182. What about the y-intercept? In other words, either b0 or a, depending upon the text or the calculator that you use. Y bar minus b1 x bar, and basically y bar, you divide the total size by n, x bar, you divide the total size by n. So y bar is summation of y divided by n, 20 divided by 4 is 5, and in the case of the x bar, summation of x10 divided by 4 is 2.5. This is how you find y bar and x bar. Plug it into this formula, y bar minus b1 x bar, so that becomes 5 minus this number times 2.5. Now notice, when I'm using this number, I'm using a lot more decimals because I want to be pretty precise. And we end up with, again, with a bunch of decimals, 5.455. Therefore, the formula for the regression equation, and we did it by hand, is y hat equals negative 0.182x plus 5.455. Now, I want to show you what we did in the previous page. We did run a linear regression t-test, and it gave us a lot of information here. I want to show you the information that it has given us. Look at this, a and b. So ti uses this formula, a plus bx, and I hope you realize it's the same formula we got here with a lot more decimals, So that will also give you the regression equation. Find the best predicted value of y when x is equal to 2. There is no significant linear correlation. The best predicted y value is y bar. We proved when we run the correlation that there is no correlation. And in that case, we have to use y bar regardless of the x value. If x is equal to 2 or any other number, the answer remains the same. I will show you when that's not the case. And also, I want you to see this. That gives you the test statistic as well as the p-value. The p-value is 0.865, way larger than alpha of a 0.05, and there is no linear correlation. This t, by the way, is refers to the regression equation and the slope of that. We're going to repeat the question here for a slightly different one. Could somebody read this, please?
I got it. Number 2, a researcher is studying the effects of testosterone injections on different lab mice. She controls the concentration of testosterone injected into the mice and measures their metabolic rates. Analyze the following data sets. Will you be running a correlation or regression? Find the value of the linear correlation coefficient R and test the claim that there is a linear correlation between the two variables X and Y.
Excellent. Number 1, we're going to run a regression. Why is that? Since she controls the concentration of testosterone injected into the mice and measures their metabolic rates. We are controlling something. Therefore, we want to know if there is an effect. There is a regression test. H0, rho equals 0. There is no correlation between the concentration of testosterone in mice and their metabolic rates. Rho is not equal to 0, which makes it a two-tailed test. This is HA or H1. HA, that means an alternative. A stands for alternative, depending on the text. There is a correlation between the concentration of testosterone in mice and their metabolic rates. And this is the claim. Now, obviously, we have the data. We're going to put them into L1 and L2 if we are using L, if you are using TI, or we put it in Excel. Either way, we have to run it with some sort of a technology. Nobody expects you to do this by hand. This is what you get. And now we're going to go to the next page and see what they mean, how we answer it according to this table. So when we continue, first we are going to write any 17, and according to the calculation from the technology, we have the R squared, and all of the above. And part 1, just as before, we are going to go with part 2, and I'm going to show you how that works. Test statistic, method 1 uses this formula. We don't even have to calculate that because this is given to us. So what is the test statistic? It is calculated here. For method 2, where we use the Pearson table, this is the value of R, which is also calculated. The next one, based on the t-test and the p-value, we go with the p-value in this case. The p-value is extremely small, 1.5316 e minus 15. That means 10 to the power of negative 15. That means the decimal from here goes to the left by 15 places. It's almost 0. It's way less than the choice of alpha, which is normally 0.05 in many cases. So if we are looking at this test statistic, it's way into the rejection region, because with n equals 17, alpha equals 0.05, R is plus minus 0.456. And this is way larger than positive 0.456. The p-value is way less than alpha, in which case we reject H0. So when you reject H0, loosely put, you accept HA or H1, so the claim becomes true. Then there is a significant linear correlation between the two variables, namely concentration of testosterone in mice and their metabolic rates. This is based on the test of hypothesis. Therefore, we conclude that there is a significant correlation between the concentration of testosterone in mice and their metabolic rates. Since this is a regression study, the significant slope suggests that the increase in concentration of testosterone in mice causes increase in their metabolic rates. This is a regression. We want to find the regression equation. Take a look at what we have here. Y hat is 199.05934x plus 379.493. How do you know that? This is the intercept. Okay, in case you're running Excel, this is how it looks like. Therefore, we can answer the following question. Find the best predicted value of Y or metabolic rates when X is equal to 1.3, the concentration of testosterone. Now remember what we do. If there is no correlation, the answer is Y bar. But we proved there is a significant correlation. So into this formula, the regression line, we plug in 1.3. So I want you to distinguish between this question and the previous one. And why we plug in 1.3. Significant linear correlation, plug in what number, whatever they gave you. And that results in 638.2697. Finally, using the above pairs and the value of R, what proportion of the variation in metabolic rates can be explained by the variation in the concentration of testosterone? This answer is always equal to R squared. If only R is given, just square it and you have the answer. Since R squared is given, 0.9869, which corresponds to what? 98.69%.